Are you saying I can go? That's already on there? Great. Hi, everyone. It's amazing how things happen in life. It was 53 weeks ago to the day and almost to the hour that I was standing here telling my Math 129 class that we weren't going to be back for a while because Michigan State had just said they were closing, and I saw the writing on the wall. So it's been that long since we've had a math seminar, and I am delighted that Alejandro has chosen to do this. I think it's wonderful. We do have a live audience here, and of course there are people watching live via YouTube, and it'll be recorded, so that's all great. And the topic today is the Pappus-Pascal Theorem, and he's got some things set up here because he's going to do real life stuff, so that's fantastic. Thank you, Alejandro.
Thank you, John. All right. So first, I want to show the sources that I'm using. One of the sources is this little book, which is printed in Spanish, a translation from Russian. And my copy is falling apart because I'm using it so much. That's my main source. The translation is from, I'm going to take this off so people can hear me a little better. The translation is from about 1980. The original book is from about 1950. Another source that I used is this Cut the Knot website. I encourage you to look at this website. It was run by Alexander Bogomolny. He passed away 2 years ago, and that picture is from that website. It is a very, very fantastic website that it is still on. People are still supporting it. And the website is interactive. You can actually go in, and this is now the actual picture of the interactive part of there's a few interactive parts of the website, but you can actually move the points and the lines will move accordingly. So that is a very exciting website to check out. A side note is that he was updating the website on July 6th, I believe, of 2018, and then he passed away the next day. He was working up to the moment or the day before he passed away. So that's a very, very good source to check out. This is another website that is worth checking out. I use this book, but I also use that website. It's much easier to look at propositions, theorems, definitions, and so forth from the elements in that website. It is organized quite well. Yeah, check it out. And some things are written a little bit in a modern language, which makes the reading a little easier of the elements. Let's go back to some history. Giza, of course, is known for the pyramids. These are the main three pyramids in the complex of Giza. And the pyramids were made between 4,000 and 5,000 years ago. Not 100 years ago, thousands of years ago. The little one is about 119 yards in length of the base. Now, to give us an idea, a football field with the end zones is 120 yards. So this is about the length of a football field with the end zones. And those are much larger, of course. Now, when we think about it, they had to know a lot of geometry to put that together. I was thinking how to put a square, a perfect square with very rudimentary tools. And actually, it's hard. It's not that easy to put a square together. If you have 4 markers and you go to your backyard and somebody tells you, hey, put a 10-yard by 10-yard square on the ground, or the markers of where the corners should go, that's not that easy. Try to do it. It's actually quite difficult. It is even more difficult if you have to position the square so that it faces south, north, or east-west. That is not easy. Imagine doing that with close to 120 yards, a perfect square. So all of the sudden things start making sense when I'm looking at the elements, because in the elements they're saying, well, if you have a point outside of a straight line, this is the way you construct a parallel to it. And this is the way you construct a right angle. Something as simple as a right angle that we take for granted is not that easy to construct if you're just out in the field with markers and that's it, with nothing else. So looking at how big of a job this is and the engineering that went into it made me realize why the elements are perhaps written the way they are, where there's a lot of constructions in it. It isn't just propositions one after the other, but here's how we do parallels, this is how we do squares, etc. All right, a little more of history. Giza is not that far from Alexandria. Alexandria is in Egypt. It is about 137 miles from here. So it's less than the distance from here to Detroit. If we walk 10 miles a day, which is doable, it's about 3-4 hours, it would take us 2 weeks to get to there. Well, for John, it will take much shorter, but for most of us, it will take us about 2 weeks to get from, say, Giza to Alexandria. It is far, but it isn't excessively far. So it makes sense to me that a lot of the geometry happens in Egypt, which is in Africa, of course. It only makes sense because a lot of engineering, a lot of geometry, and by geometry I mean building large things, happened in Giza. It makes sense that the hub of geometry was in Alexandria. Yeah, so that is something, in my opinion, very, very interesting, very revealing, that how, one thing may have led to another thing. By the way, the Elements has been written in very, very old Greek. And that is very hard to read, even for Greeks. I know two people who are originally from Greece. I showed some of the writing of the Elements, the original writing of the Elements from this book, to one of them, and he says, the first one says, oh, this is too old, I cannot read it. This other friend reads the Bible in Greek. He probably knows what it says. I show it to the second friend, and he says, this is really old. It's very hard to read. He was able to actually corroborate that the translation was quite accurate, actually, the translation in this book by Thomas, Sir Thomas, what's his last name? Tiff, thank you. All right. Oh, but the reason why I brought that up is because there are more modern axiomatizations of geometry, and these are some of them. So these are some of the axiomatizations, modern axiomatizations of the Elements. It's probably a good idea to check them out. I don't know why people don't use them too extensively. Maybe because the Elements is there and we can just check the Elements instead of checking the more modern reviews of geometry. I put a blank here because I wanted to point something out. Do you guys know where Overijssel is? It's Allendale County, which is here in Michigan. So George Birkhoff is actually from Michigan. I just wanted to point that out.
Can I throw in something real quick?
Yep.
He was taught in Chicago by someone who eventually came to GRJC and taught math.
Oh, wow.
Yes.
Oh, wow.
That's it.
Interesting. Yep. So the chronology of what I'm talking about today, has to do with Euclid, Menelaus, Pappus, of course, some people who introduce projective geometry, and of course Pascal. It is said that Pascal proved the theorem, his main theorem, when he was 16. That's quite young. And then these guys, which are the authors of this little book, gave us a good twist to the theorem, a good way to approach the theorem. I came up with a diagram that probably shows this a little better. So there's the elements. That's the start of everything here. Then there's Menelaus, came up with a theorem. Pascal, well, let's start with Pappus. Pappus came up with this theorem with straight lines. This has to do with hexagons, 6 sides. 6 sides again, but on 2 straight lines. And then Pascal came up and said, well, we can do this with a circle, and then thanks to projective geometry, we can expand that to the ellipse, hyperbola, and parabola, of course. I'm not sure. I think a lot of people take this for granted. It's almost an exercise now to do this part starting with Pappus and using projective geometry. What these guys did, though, is they bypassed Menelaus. They went from the elements to finite case with parallel lines, and then they used projective geometry for the general case. And this is what we're going to go through, just this part of it. So finite with parallels, projective geometry, and then we have the general case. That's how we're going to address this, show this theorem. And then we're going to do an application here in the classroom. So first, let me go over some quick concepts of geometry, the line and parallelism. Those are the 2 places where Euclidean geometry and projective geometry diverge a little bit. Not too much, but a little bit. I understand that in the Egyptian world, they did not care too much about infinite lines that go on and on forever. They were very practical. They were engineers. They put big structures together, and they put them together very well. So they were practical. Okay, I need a segment. I need a stone this big and this wide and this tall. They don't care necessarily about infinite lines. They just care, hey, I need this square, this rectangle, this triangle, this circle, whatever. We need things that are segments. In contrast, in projective geometry, we use infinite lines, and pretty much only infinite lines. There's a couple ways in which we can support the idea that in the old geometry, we only use segments. One way is because of the definitions. The definitions suggest that's the way it is. For instance, they talk about the ends of a line, implying that the line probably ends. When they define right angles, they put a line on top of another line. Well, that makes sense if we are talking about segments. It wouldn't make as much sense if we were talking about infinite lines. All right. Parallel lines also suggest, the way they define parallel lines also suggest that they are not talking about infinite lines. This could be argued a little more, though. They just say indefinitely instead of forever and ever. So that means, extend it a little more and the lines won't cross. And extend it a little more and the lines won't cross. And in my opinion, that's the way they defined parallel lines, not go on and on forever. So let's talk about projective geometry. Oh, in projective geometry, the proofs in projective geometry are very cool because if you can prove something in a very finite way, you can easily extend that to many different cases without using any kind of measurements. Let's talk about how to project things onto other things. So this is the way we project a line onto another line. We can project this line onto this line or the other way around. It doesn't matter. There's a one-to-one relationship between the points. So it doesn't matter which way we do the projection. So this point and that point on the other line go together. There is a one-to-one relationship between those 2 points, and here, and here, and there, through the point S. So that is a basic projection of points from one line to another line. There is another projection. So the 2 points don't have to be on the same side of the line. They can be on the same side of the point. They could be on opposite sides of the point. So we can have a point here, the point of projection, and then the corresponding projected point here. So it can go either way. Whichever way we do it, there's going to be a one-to-one relationship between points on this line and points on this line. But there's a twist. What if the lines actually cross each other? Well, we can do the same thing. We can project this point onto this point, and the 2 points are on the same side of S. And likewise, we can project this point onto this point, or vice versa. But here, wait a minute. No, here, this is the case, where the 2 points are opposite sides of S. Yeah. So this gets a little more tricky because sometimes points that are connected with one another are on the same side of S, and sometimes they're on opposite sides of the projecting point. Now, something interesting happens. What point is projected to E? Assume this dotted line is parallel to this line. So the question is there it seems like there's no point that goes with E. I mean, you can project on any point, but nothing with E. However, if we move Z up that way, the corresponding Z here will move closer to E. So it would make sense to connect the line with a point at infinity, a point that is far, far away forever, and that point is going to be connected with E through this projection. Now you may say, well, if we move this A towards E, then this point is also going to be farther and farther away this way. Okay, so the same point that is attached to E over there on the upper right corner is also going to be attached to E if we move the point far on the left lower corner. So when we extend a line in both directions, we're going to have a unique point at infinity that is going to be connected with this point E. Yep. And vice versa. What about this point D prime? What point on this line belongs to D prime? Well, again, if we move C to the right forever and ever and ever, we will get closer and closer to D prime. So there's going to be a point at infinity on this line that is going to be connected to D prime. So what is happening when we project lines is that two things are happening. One, we have a point at infinity that gets added to the line. And two, there's a shift of points. The points are shifting. So there's a point at infinity that goes with E, the infinity on this line. And then there's a point at infinity on this line that goes with Z prime. I'm sorry, with D prime. Yep. So this is what's going on. This is my way of explaining what's going on. We can extend a line forever and ever in both directions, and we're going to end up with one point at infinity that is going to connect the entire line in both directions. I know that's it is sort of a circle. We're kind of forming a circle, but it's not a circle, sort of. Something that happens with projective geometry is that two parallel lines are going to converge, which is divergent from, or it is different than what happens in Euclidean geometry. Two lines converge at the point at infinity, at one point at infinity, exactly 1 point, not 2 points, but 1 point at infinity. So all the lines that are parallel to a given line converge at the same point. As a consequence of that, every time you have two lines, they will cross, either at an ordinary point is just an Euclidean point, or at a point at infinity. So this would be the point at infinity case. This is just an ordinary point where they cross each other. And we're going to add one more element to the projective plane, and that is we're going to add the line that consists of all the points at infinity. So all the lines that go in one direction have 1 point in common at infinity. Change the angle. All of those lines that go in that direction are going to have 1 point at infinity. Change the angle. All of those lines that are parallel are going to end up at 1 point at infinity. All of those points together are going to make up one more line that is at infinity. Those are just the same definitions and propositions I just put together. The first thing that came to my mind when I was looking at this is, well, is this a sphere? Are we doing geometry on a sphere because we have sort of circles? And the answer is no. Because when you have two lines on a circle, or rather on a sphere, we have 2 points of intersection. But we cannot allow 2 points. There's only 1 point of intersection between two lines. Then I started thinking, I don't know how I started putting together the Cartesian plane with the projective plane. How would this look, the y equals 1 over x that has two asymptotes? And as we go to the right, we get closer and closer to 0. As we go on the left, we get closer and closer to 0. How does that look if we were able to do this projectively? And that's what I came up with. So this is the vertical asymptote. There's no horizontal asymptote because infinity actually is a point in the projective plane. And so as we approach infinity on one side, we get to 0. And as we approach from the other end, we get to 0 also. So that was just my interpretation of 1 over x in the projective plane. I thought that was interesting. Let's move on to projecting onto a plane. We can project onto a line. We can project also onto a plane. How do we do that? Take a point off the plane, project it with S, with a straight line going through the outside point into here. When it hits, that's the projected point. So you can project several points. You can project a whole entire line this way. So this line, whichever angle it goes into relative to the plane, will project perfectly into a line here. The point that is at the same level to S relative to the plane, so at the same distance from the plane as S, will project into the corresponding infinite point on the projective plane. So everything works pretty well. And points that go up here, above S are going to project back there. Everything is going to work fine. Points that are closer to D are going to project closer to this point. We're assuming this point is way out at infinity. So we're bringing infinity closer to us. That's what we are doing, essentially, with projective geometry. That's pretty much what I was mentioning. This point gets projected at this point at infinity, this particular point B. And then the point that is at infinity here on the other line is going to be projected into this point here. So everything is going to be matched perfectly. Every point is going to have a frame through projections. That means we have to bring 1 point at infinity, which goes in both ends. Okay. We need a theorem. The theorem should be fairly short. Any line projects into a line. Any line in space projects onto a plane into a line. The proof is very straightforward. So if you have a line, you can pick 3 points, 2 or 3 points. So this point outside of this line and those points form a plane. You can just come up with a plane. And when we intersect two planes, we end up with a line. So that is very straightforward. This picture is from the book. I was going to produce the same picture, so there's no point in producing the same picture if it's already on the book. So that's why I gave him credit there. And if the line happens to be at the same level as S, then where's this line going to go? Of course, at infinity. It's going to be projected. This line will be projected to the corresponding line to infinity here on this plane, on this projective plane. So lines go to lines. That's the main thing about this. This is a neat picture. Sometimes projection is called perspective. Perspective picture. Of course, I took it from Britannica Encyclopedia. It's a neat picture that shows how the projection happens. So we are projecting this triangle onto this plane, and that's exactly how it happens, using a point. Of course, pictures do get more complicated than that, but that's a good picture to show how we project things. Okay. We're not measuring anything. Everything is just by points. And what we are looking at is the incidence of points on lines and lines on points. By the way, there is a dual principle. I'm not going to get into dual principle if you're interested. Most places where you look at projective geometry, you're going to see the dual principle. Milanaus, I wanted to show you a little bit of the theorem. This is the theorem. Essentially, what it says is that if those equations are correct, then these 3 points are collinear, and so are these points. We're going to bypass this because we're not going to use Milanaus, but I wanted to show you what it says. Anyway, let's move on to what a hexagon is. That's a normal hexagon. Here's a picture of it too. The one thing we want to be aware is that there are opposite sides to the hexagon. So AB is opposite to ED, and we're going to have this standard lettering of the hexagon, A, B, C, D, E, F, without skipping any. So AB is opposite to ED, BC is opposite to EF, CD is opposite to AF. So just remember that, because it's going to get messy once we start doing things with other hexagons. For instance, this one. This is also a hexagon. And so we can kind of see that this is opposite to that. Which one is opposite to this one is not so clear. It's this one. As you can tell, that is not as obvious, because one may think, hey, wait a minute, isn't this the opposite? That's why we got to keep this in mind, because the opposite of CD will still be AF, regardless of how this gets manipulated. That's even worse. I mean, the only ones I can tell are opposite, I think, are those two, and only because the drawing kind of shows it. Which one is opposite to that one is not as obvious, or that one. But just keep that in mind, that we're going to be talking about opposite sides of an hexagon. In projective geometry, we don't have necessarily segments. We have just lines that go on and on forever. So a triangle is going to look like this. That's a four-sided picture. Now, it is interesting because somebody may say, well, a minute, there's a point here. No, no, no. Those are the vertices. And this is that just happens to be a point where two vertices, two sides cross. But that is not a vertex of the figure. So we have to distinguish vertices of the figure versus places where sides of the figure cross, because the lines go on forever. Yeah. So this is a hexagon. Again, a figure of 6 sides. That's another one. And you can tell by the number of vertices there is. 1, 2, 3, 4, 5, 6. So there's 6 vertices So we have the same kind of figure as this one. So those two are the same kind of figure. Again, that's a six-sided figure. Here's where the labeling of it, or one labeling of it. We have A, B, to C, to D, to E, to F, back to A. So there is the same kind of situation as here. Who is opposite to A, B? Well, its opposite is going to be ED, as here. ED is opposite to AB. Who's opposite to EF? Well, CD is going to be, or rather CB. Let's see, CB is opposite to EF. Yep. And then the two lines that are not dotted or thick are going to be the opposite of each other. Yep. In addition to that, those lines are going to cross. So for instance, eventually those two lines are going to cross at a point P. Those two dotted lines that are opposite to each other are going to cross at a point Q. Even if they're parallel, they're going to cross at infinity. And those two lines are going to cross at a point R. So we're going to look at the crossing of opposite sides of this hexagon. So the theorem, we're going to get into the theorem. If the points, alternating points, so if A, C, E happen to be on a straight line, and B, D, F happen to be on a second straight line, then the points P, Q, R are going to be on a straight line. That's what Pappus Theorem says. Okay, so here's a hexagon. So pretend there is A, B, C, D, E, F, back to A. That's a hexagon. This is the way the program I was using put colors in it, black and white colors. I thought that picture was cool, so I just left it like that. But again, this is a hexagon, A, B, C, D, E, F, back to A. So this is what the theorem says. If alternating points A, C, E, A, C, E are on a straight line, and then the other alternating points B, D, F are on a second straight line, then the opposite sides are going to intersect, and the intersections are going to be on a straight line. They're going to be collinear. So here's the intersection of two opposite sides. Here's the intersection of two opposite sides. There's the intersection of the other opposite sides. And then there is the, then we show that they are on a straight line. By the way, you can see this picture in different ways. Somebody could say, well, what if we take the points as here and here? Well, then those are the intersecting points. Or you can take the points on this line and that line. Well, those would be the intersecting points. So actually, this theorem can work in different ways. Yeah. So how do we go about proving this? I believe Pappus just proved things in the finite way using Menelau's theorem. That's what people believe. However, these guys came up with a quite clever way of coming up with a proof of the theorem bypassing Menelau's, just going through the elements using projective geometry. In this case, we have to split the theorem into three cases. Two sets of opposite sides are parallel, in which case the third set is also parallel. Only one set is parallel, or all 3 points cross, none of them are at infinity. Okay. So we're going to prove the first one, this one. If two sets of opposite sides are parallel, then the third side is parallel. The third set of opposite sides are going to be parallel. And we're going to further split that into two subcases. The two lines where the alternating vertices lie are parallel and the two lines are not parallel. Let me show you. Okay, so we're going to assume those two lines are parallel. Whoops. Oh, we're going to need another theorem but we're going to assume that those two lines are parallel, and we're going to assume that two sets of opposite sides are parallel, and we want to prove that the third side is parallel. We need some propositions from the elements, proposition number 33 and number 34. The reason why I put an asterisk here is because according to Joyce, one of the references from the beginning of this presentation, in the elements, we never defined what a parallelogram is. They just started using the word parallelogram without definition. So the elements are not as perfect as we think they are because they have a little bit of gaps. I think it was Birkhoff who said, I'm not sure, but no, I better not say who said it, but somebody said that the elements is also missing the concept of betweenness, which was addressed later by a modern mathematician. So the elements are not as perfect as we think they are. They're pretty good, don't take me wrong. They're still a good standard, a good foundation, but they're not as perfect as we think they are. And you can see some evolution in the elements. Here we have a proposition, an if and only if proposition really in two pieces. Later on in book 6, there are propositions that are if and only if propositions. And that makes me think, wait a minute, maybe they evolved in the way they wrote the elements because it's more efficient to have if and only if propositions than just propositions going one way and then another proposition for going the other way. Anyway, let's assume that two pairs are parallel. Pretend those two are parallel, pretend those two are parallel. We want to prove that those two are parallel. Well, if you cut parallels with parallels, the corresponding segments that we end up with have to be the same length. So because those two are parallel, this top segment has to be equal to this lower segment. Because those two are parallel, this segment is equal to that segment in length. So if we subtract, that means that this segment is equal to that segment, which means that we have a parallelogram, and correspondingly, those two are parallel. So it's basic geometry from the elements. And so we have proven that if two sets of opposite sides of this six-sided figure are parallel, then the third set has to be parallel, assuming they are alternating vertices on straight lines and assuming those lines are parallel. What about the case when they're not parallel? We need another theorem. Book 6, proposition number 2. This is the one that made me think about the if and only if and then propositions. This is an if and only if proposition in one statement. Why in book 6 they bothered to do if and only if propositions, and in previous books they didn't. I don't know. Maybe it's a coincidence. I don't know that. But it makes me think maybe they were evolving in the way they were writing the elements. By the way, a side note is that I think this was the contribution of the Greeks in Egypt. I think the Egyptians already knew a lot of the elements. That's my guess, based on what I'm observing. And the Greeks were very much into why. Why are we doing this? Why are we doing that? So I think they came up with the axiomatization of the elements. Yeah, I think that was the contribution. That's only my speculation. I don't know that for a fact. I wasn't there. But that is my thinking, that's how the Greeks contributed to the elements. The Egyptians were very practical. They were building things. They were putting things together. By the way, the Chinese also were very practical thousands of years ago. They have a lot of tables that they used. Anyway, I digress a little bit. So we want to show that if those two lines intersect at an ordinary point, so they're not parallel, then if we have two sets of parallel lines, then the third set is going to also be parallel. Here is what's going on. We're going to assume that the 2 points intersect at O, the point O, far away. And so we have those triangles. The math is here. I don't want to dwell too long on the computations, but we got to, because of being parallel, we have similar triangles, corresponding ratios between the two sets of triangles. We have BO and EO are the same, so then we can make those two sides equal to each other, divide on both sides. We have a relationship, a ratio, a proportion, and consequently, those two sides are parallel. It's a fairly straightforward computation. Actually, I don't know if there's too much of a computation, just the cross product. If those two are equal, then those two have to be equal, and then divide on both sides, and voila, we're done. So it's a fairly easy computation. So we have proven Pappus theorem in the case two lines are parallel. No, two sets of opposite sides are parallel. We have proven it. Why? Because that means that the points they intersect at an infinity, all of them, and consequently the points are going to be on a straight line. Okay. So now we're going to use that to prove the general case. We need a lemma, quick lemma. Any line can be projected on a projective plane, can be projected into another line, into the line at infinity at another plane. We can always do that. Take a point S off the plane at random. It doesn't matter as long as it's outside of the plane. Notice this plane of the line and the point. Come up with a plane that is parallel to this plane. That's it. We're done. Every point on this line will project through S onto the plane to infinity. Because a point here will project onto the plane. I'm kind of curving it, but because this is not large enough. But if we had a point here on this plane, beta, it will project into a point here. And if we have a point there, then S will project this point here into pi somewhere down here, because this plane keeps going down this way. Yep. So we can always project any line onto the infinite line. We can always do that. All right. Yeah, we're going to use that. And here's the way I'm going to show you how we use that lemma to prove Pappus in general. So this is a general, just six-sided figure where three vertices are on one line, three vertices are on the other line, and that's it. We don't know anything else whatsoever about the six sides. We don't know if the opposite sides are parallel. Clearly here they're not. They're not, All right. So those two lines are going to meet somewhere at a point P. Where? We don't know. They're going to meet at P. Those two lines, this one and that one, are going to meet at Q. And the other lines are going to meet at R, PQR. Now take the line PQ and project PQ onto the infinite line on another plane. This is a second plane. We can always project from here into here in such a way that PQ projects into infinity. So this line, pretend that's the line of infinity. Well, what happens if two points are infinity and they're the intersection of two sides? Well, those two lines have to be parallel. If this is infinity, those two lines have to be parallel. And those two lines have to be parallel. I lied. These two lines have to be parallel. P, the ones that make P, and the ones that make Q have to be parallel. But we just proved that if you have two sets of opposite sides that are parallel, then the third side has to be parallel. So R has to be on the same infinite line. That's it. Because the projection back puts PQR on the same line, because lines go to lines, no matter what. When we're using projection, lines go to lines. That's the proof. That's the proof. Yeah, so all we had to do is prove the special case of parallel lines, project the general case into something like this, project back, and we're done. And by the way, that is the very spirit of mathematics. That's the way we do a lot of things in mathematics. We take a structure, we map the structure into a different structure where we know how to work in that structure, and then we map back the results. That's exactly how a lot of the mathematics we do works. This is the picture in this little book, by the way. I did not want to draw that picture because it's quite messy. Here you see, well, sort of see the original six-sided figure. Here is where they become parallel, and then they show the PQR. As you can tell, that was kind of messy, so instead I just split it up into two planes instead. Way, way easier to visualize, in my opinion. This is a very good picture because it is even more accurate, but then it's harder to see. Oh, the application, real quick. We barely have enough time for the application. So one application is this. In art, oftentimes when you are drawing a picture, you don't have enough room to draw the intersection, which is okay. And then you want to draw a new line that is going to intersect to the intersection of those 2 points, rather, of those 2 lines. So which way are we going to draw if we do not see the point? If you have the point available, you can, of course, draw the point and then draw the line from this point to the point of intersection, and then you're set. That's easy. But if the point is not available, how are we going to do that? That's not easy. And this is the equivalent. So pretend you got a line, 2 points define a line, so there is 2 points, so there's a line. Pretend you got another line here. Let's do this. So there's another line, and they're going to converge somewhere. And pretend we want to draw a line. You know, I didn't have spots anywhere on the floor. These are just kind of random places where I'm putting those markers. And by the way, thank you, Mike, for getting this text. They help a lot. So the question is, how do I get a line that goes to the point of intersection of those 2 lines if I cannot access the point of intersection? The point of intersection is probably in the next classroom. And by the way, they had to do that in engineering. They have to think about roads that converge to a point, and you want to start a third road, and you want the road to converge to the same spot. How are you going to start building if you don't know which direction to go? Very, very important. So how do we do this? We're going to do it here without measurements. And this is, let me show you the picture first. So we're going to draw those lines. Draw means just making sure that things line up correctly. Those 2, we're going to come up with those 2 intersection points. We're going to draw lines this way and this way. This point of intersection will be the one that's going to line things correctly. I'm labeling the letters A, B, C, D, E, F, because the hexagon is not clear. Some of us may be thinking, oh, so those are the 2 lines where the 3 alternating vertices are going to lie. No, that's not the line. Those are not the lines. Those are the lines. Those are the straight lines that we're going to use, where the 2 pairs of 3 vertices are going to be on. So this is the hexagon, actually, that we're working on. Same pictures. That is the exact hexagon that we're working on. Yeah, that is it. And so A, B, C, D, E, F, back to A, E, and C are on one line, A, E, and C, which alternate. Whoa. A, E, and C. Yeah, yep. A, E, and C, and then B, D, and E are going to be on the other line. When we look at the opposite sides, those two are opposite sides. Those two are going to be opposite sides, and those two are going to be opposite sides. Sure enough, they converge in the same point. So I'm going to need 2 volunteers to help out, please. Oh, Mike, maybe. And one more. Oh, Kurt. Kurt is going to help us. Okay, thank you. So first, we need somebody to stand behind that, please. So you're going to look at that line, those 2 lines. We need, and then you're going to be behind that one, Mike, please. And then both of you are going to tell me where to position this so that, so that it lines up? So lines, those 3 line up, and those 3 line up. To the right.
That's good.
Okay, we're going to do the same, but now Mike, you're going to be there. And instead of looking at this, Kurt, you're going to look down this way. And you're going to try to look at those 2, Mike.
That way a little.
Good? Mm-hmm. All right, one more, because we got those 2 points. Now we need the intersection of those 2. So the new ones. Okay, so I need you, Mike, here, Kurt over there. Is that right? Hang on a moment. Yeah, you guys are good. So the new points, you're going to look at those 2, and you're going to look at those 2, Mike.
What, 2?
Yep,
Sorry.
those 2.
Okay.
And then you're going to tell me where this intersects. Where this lines up.
Let's say good.
I think.
And so then this line here.
Yep, is going to converge. So that original point, Parker, and this one are going to converge where those 2 original lines went. No measurements, no trigonometry, no algebra. There it is. And I tried to do this with algebra and trigonometry. It was messy. And you need an origin. If you are using the Cartesian plane, you need an origin. You need to measure things. You need to round things. You need trigonometry. Eventually, you're going to round things, and things are not going to be exact. This is so clean. I cannot even start thinking, wow, this is few observations, and voila, we get it done. So I was completely impressed by these constructions. By the way, there are many constructions that are way more complicated. This is probably the easiest one. This is one that I saw in this book. There is about 2 or 3 constructions, and they are way more complicated. And not to mention there is the dual. There's much more to projective geometry than this. This is one of the easiest ones to visualize. And that's it. That's the end of the presentation. Thank you. Thank you.
Do you have any questions for our speaker this afternoon?
Yeah. And if anybody wants a copy of the PowerPoint presentation, just send me an email. I'll send it. I'll reply with a copy. No question. No problem. Yep. Thank you, guys.
So is there, so you were talking about projecting onto a line and then projecting onto a plane, so then the obvious question is, do we go up to higher dimensions?
Could you repeat the question, because you got that?
Sure. So the question is, can we generalize from lines to planes to higher dimensions,
Hyperplanes.
hyperplanes? I don't know.
I don't either, that's why I'm asking.
That's my answer. I'm guessing yes, but I actually don't know. No. And we also have to see where this, the question is a great question. We have to also see where this came from. This came from building things, from the Egyptians. So probably they weren't thinking too much about that, even though it is an excellent question to ask. How would this work in 3-4 dimensions, hyperplanes? Yes. And I don't know.
Okay, well, thank you again. And I'm not sure what our status is for the next talk. Will there be one in April? At the moment, there's none planned. If you, or anyone you know, would like to give a talk in April, contact anyone in the math department. I'm John Dersh. You can contact me, but anyone in the math department would be happy to pass the information on. Thank you all for coming. Those of you who are watching virtually, thank you. You are the first to do so in this setting, and we appreciate it. And thank you to class for everything he does for us.